Um, all right, so let me just see if I can connect my iPad.
And so, Sada, you have about 25 minutes from now.
Okay, yeah, sounds good. Thanks. Okay, so this talk is about accelerating auto-tuning. It was mainly done by PhD students Chendi Lee and Yufan Zhu and Sina. All of them are PhD students. Main contributions were by the first two authors. So I'll start with motivation for why auto-tuning is quite popular. So if you take a tensor operator to be optimized, essentially there are three overall options. You can use a vendor library or an auto-tuning framework or compiler optimizations. And this slide is basically from the original TVM paper that pointed out that they've developed this auto-tuning approach that enables higher performance than a high performance vendor library like CUDNN or compiler optimizations, that time a state-of-the-art polyhedral compiler, the tensor comprehensions from Meta. So just to give you an example, using TVM auto-tuning, what we see here is the pipeline of operators for the ResNet CNN. And for various operators, if we look at the performance that's achievable on, and this is on an RTX 4090 GPU, by the vendor library CUDNN versus something that's optimized by TVM, you can see that there can be significant potential for speed up. Now, of course, here we are not comparing apples to apples. CUDNN is a library which can perform convolution for arbitrary shapes with respect to the input tensors, whereas what auto-tuning with TVM does is to take a specific fixed problem shape, such as here we have the size is fixed at 56 for the H and W, and the convolution is the channel sizes are also fixed, right? So essentially, it's feasible to perform auto-tuning by evaluating a lot of possible configurations. And that's the reason why it's feasible to get higher performance for these fixed shape operators compared to a library which is intended to be used for arbitrary shaped or arbitrary sized operands. So the pros and cons with TVM, auto-tuning is advantages. It's very easy to use and it generates very high performance for the generated GPU kernels. But the primary drawback is really the high auto-tuning time. It takes roughly 15 to 30 minutes per layer in a pipeline. And so if you want to optimize for the full pipeline, it could be several hours to days. And second disadvantage is that if you were to run the auto-tuning for the same operator multiple times, you don't really get the same performance. You can get some variability. So first, with respect to the auto-tuning time, so here is a set of benchmarks that we've evaluated it on, some set of matrix multiplication kernels, some convolution 2D kernels, including 1x1s, 3x3s, various strides taken from two full networks, the YOLO 9000 set of kernels, and for ResNet 50s, all of the convolution kernels. So you can see that it just takes between 10 to 30 minutes per kernel for the recommended number of configurations to be evaluated that's recommended by TVM, which is 1,000 trials. On this slide, we see the example of the variability. The red dots and the blue dots represent the trace with respect to the performance achieved as a function of the number of samples or trials. And I'll go into more detail with respect to what these trials mean. And as we can see that as we go through time, we get increasing overall average performance, even though you can see that even late in the stage, you can have some instances that are expected to have high performance, but they really have low performance. So essentially, TVM, as we'll see, performs a sampling in the big space of possible tile loop configurations, and then a subset of them that are the most promising are actually the code is generated and it's evaluated. So you can see that here the blue run achieved a higher peak performance compared to the red run, roughly by about 20%. So the goals of this work were to see whether we can address the two main disadvantages of a TVM's autotuner, which is one is, can we decrease the total tuning time without much loss in performance, and can we reduce the variability across runs? So the answer is yes, we can achieve a significant reduction, roughly an order of magnitude, to get about the same quality of the tuned kernels. And second, yes, we can also reduce the variability. So sorry about that. So now I'm going to spend a little time, just don't expect many people are familiar with the details of how auto-tuning works in TVM. And therefore, I'm going to spend a little time going over that before I go what were the optimizations that we implemented. So this slide shows the overall flow with TVM, starting with a high-level model representation. It lowers it into a graph-level IR for TVM, which is then lowered into a tensor expression level. An example of that is seen on the right. So the tensor expression is specifying a MAC-mult in this example, and it's saying that the problem sizes are N and M, and it's not the complete specification. There's also a K, the reduction dimension, and the computation is specified as a lambda running over IJ. For all I, for all j, we are performing the dot product essentially of aik times bkj. So that's specifying what the computation is. And what TVM does is, for given this high-level representation of the computation, it generates a big search space of tiled configurations, and I'll show some detail. And then it searches for an optimal configuration in that space. So here is a slide that just gives a little bit of detail. So the MAC-mult, if you can think of matrix multiplication normally as a triple nested loop over ijk, if we do tiling, then we increase the number of levels. And what is done here is to have 5 levels of tiling for every parallel dimension, where in this case, the loops I and loop j are parallel loops, and 3 levels of tiling for every reduction loop. So this is a systematic process. Given any such expression, TVM will expand it using this schema. And so here, for example, we have, and these levels in the nested loop, tiled loop, get mapped to different aspects. So for example, we have the parallel level tile level 0. These are, there are undetermined tile size parameters at this point, and those are going to get mapped to thread blocks in the GPU code. Then if you take the level 2, that essentially maps to the thread index .x, which means it's mapping to threads in the thread block, and so on. So we don't really need to understand the specific details, but just at a high level, we have a multi-level tiled schema, which maps with a way to map that to a GPU kernel. And so essentially, what is undetermined at this point is the values of these tile sizes at these various levels. So in this example, we basically have these 5 times 2, 10 tile for the I and j, and then another 3 tiles, so 13 tile size variables over which we are going to be trying to do the auto-tuning search. So the overall search process is illustrated here. So we start with an input specification of the matmult operator with specific problem sizes. Like in this case, we are doing a 256 by 128 by 64 matrix multiplication, for which we want to generate a tuned kernel for a GPU, for the target GPU. So the first step is the search space construction, which I illustrated before. So essentially, that search space you can think of as having a large number of possible points, where any point in the search space corresponds to some configuration of tiles in this tile size vector. Now I'll explain what the feature vector is in a minute. So once we have the search space constructed, we basically there is a way of exploring the search space for promising candidates, and those promising candidates there could be 100,000 to 10 million possible candidates, and the whole task is to say which of those should we actually try to create code for and run and evaluate. So the process is you generate code for some promising candidates, make measurements on the target platform, and then based on that, there's a database of these configurations and the performance achieved by those configurations, and a XGBoost machine learning cost model is generated, and then that is used in successive iterations to search for this. So essentially, the configuration so the performance model is based on extracting from the multi-level nested loop code. As essentially, the configuration is a set of tile sizes, but a large number of features are extracted, which involve things like what are the total operation counts, what are the buffer sizes, and so on. So a large number of features are extracted, and those are used in the model that is going back to the slide. So that's essentially the cost model is an XGBoost cost model, and that's used to sample in this large space to find, based on that cost model, those that have the highest predicted throughput. Those are the ones that are actually selected for actual code generation. Sorry about that. All right, let's All right, so now let me quickly go over two optimizations that we implemented. So one of these was to replace these syntactically derived feature vectors that answer uses, instead with some analytically derived components that I will explain on the next slide. And the second was to replace the genetic algorithm-based search space exploration strategy that's implemented in Answer by a neighborhood search algorithm. So the first optimization was to use analytical modeling to estimate for a given configuration various key factors that affect performance of a GPU kernel. So one of them is, first one is operational intensity for the amount of data moved from global to shared memory. Then operational intensity with respect to shared memory to register transfers. And the third is the operational intensity for the stores from the registers to global memory. And then concurrency metrics of instruction level parallelism, warp level parallelism, and estimated occupancy. So essentially, data movement and concurrency are key factors that affect performance of GPU kernels. And for a given set of tile sizes in that schema, we can analytically, and the details are in the paper, you can figure out these operational intensities. And a final metric was a wave efficiency, which has to do with how effectively the set of SMs, the set of thread blocks maps over to the set of SMs. And the second optimization is to replace the genetic algorithm-based search strategy with a neighborhood search, where here we are seeing this neighborhood search in the tile configuration vector. In the simple example, we say, assume we just have 3 tile sizes along I, J, and K. We essentially we start at a random configuration and then predict performance of 1-hop and 2-hop neighbors in a d-dimensional tile space. So in the example I showed, there's basically 13-dimensional tile space. And then evaluate the top K, and then K is a parameter, to actually compile and execute. If you find a better configuration, then we essentially move to that configuration and essentially slide the window and evaluate the next K. And then there's some thresholds to abort or terminate search and start from a new random point if we get stuck. So this slide is essentially showing an example of that flow. So the orange shows the predicted score, and we are starting at the gray point, and then we look at all of the neighborhoods, and then we look at the top 2 predicted scores, we evaluate those, and then the evaluation may or may not exactly match the prediction. And then the one among the evaluated ones that has the highest, if it improves on the current one, we basically move. And that's essentially the idea behind the neighborhood search algorithm. So, I'll go to evaluation. So we compared the default TVM answer scheme with a few variants. We essentially have these 2 optimizations. Optimization 1, which is called AF, which is used the analytical features for the XGBoost model instead of the default features of TVM answer. And the second is dynamic neighborhood search, DS, which is optimization 2. And then we can also combine them both, and then that's answer AF-DS. So we basically evaluated these 3 versions: answer modified with just AF, answer modified just with DS, and answer modified with AF-DS. And we performed 3 runs for each of the benchmarks on 2 platforms and measured the mean and the variability. And so the best achieved performance was measured after 1 minute of wall clock time with auto tuning and 2 minutes of wall clock time of auto tuning, as well as a full 1,000 trials, which is answers default. And the kernel performance measurements were using the Insight Profiler. So the experimental evaluation on these benchmarks is essentially a bunch of matrix multiply kernels from BERT, base and large, and all of the convolution kernels from 2 pipelines, ResNet 50 and YOLO 9000. So this slide shows the performance of the combined optimizations. So the green bars represent what answer does, and with both, we basically show what is the performance achieved in 1 minute, 2 minutes, and after 1,000 trials. The X or the star represent the after 1,000 trials, whereas the shaded the bars, the light colors represent 1 minute result, and the darker is 2 minute result. So the results here are for the 4090, the results for 3090, and for the other cases are all in the paper. So what we can see is that we get comparable or better performance in 2 minutes, that's the dark maroon, than answer 1,000 trials, which is basically the green cross, quite consistently across all of these benchmarks. And for more than half of the benchmarks, even after 1 minute, we are actually able to get a better performance than the 1,000 trial based, which roughly takes 15 to 30 minutes with answer. So the evaluation of variability, the metric here is to look at across these 3 runs, look at the maximum achieved performance minus the minimum divided by the maximum performance. And again, with this, we can see that even in 2 minutes, the variability across runs is lower than the variability at the end of all 1,000 trials of answer. And if we go all the way to 1,000 trials, the variability is quite a bit lower. Okay, so then I'll summarize. So TVM answer generates high performance kernels, but auto tuning time is high, and variability of performance of the tuned kernels is also high. And we implemented two optimizations, one to use analytical features instead of the syntactically derived features from in answer. And then we used a new sample neighborhood search and evaluated around 30 benchmarks on two platforms, including matrix multiplication and convolution. And we achieve comparable or better performance in an order of magnitude less time and achieve lower performance variability. All right, I'm done. I'll be happy to take any questions if we have time.
Yeah, let's thank Sadar. And yes, we